Jonathan is passionate about developing cutting-edge tools to enhance the developer experience and reduce time to market. He's a veteran of several San Francisco Bay Area hardware startups. He enjoys wearing many hats and doing whatever it takes to bring high-quality products to the market, from proof of concept through mass production. And above all, he wants to share his enthusiasm for developing advanced and embedded system with as many as other engineers as possible.
I'm really happy to be here. As Michele mentioned, my name is Jonathan. I'm the founder of Bino LLC, and I'm a member of the MIPI I3C working group. Today, I'll be talking to you about coming to grips with MIPI I3C testing, debugging, and conformance. I have put together a brief agenda of what we'll cover in today's session, starting with MIPI I3C test tools and techniques. We'll talk a little bit about what it means to debug protocols on top of I3C. We'll cover the topic of compliance testing in I3C Conformance Test Suite. And we'll also speak briefly about the MIPI I3C interoperability workshops, also known as the MIPI I3C plugfests. And then we'll wrap up the session by opening it up to the audience for a question and answer session. So let's dive right in. The first thing that we'll cover are I3C test tools and techniques. So thankfully, the market adoption rate of I3C has already led to the situation where we have a variety of different test tools that are available on the market today. There's devices that are available in a few product categories, including protocol analyzers and exercisers, logic analyzers, host adapters, oscilloscopes, and one other category of devices that we should really consider as a tool available for our usage are dev boards and eval kits coming from the semiconductor manufacturers who have already implemented I3C in their devices. Each of these categories has different strengths, weaknesses, capabilities, and techniques that you can use with that to help implement your own I3C implementation. Let's dive into a few of these and look at the highlights. The first category of devices that I'd like to speak about are protocol analyzers and exercisers. These are devices that can exercise the full I3C protocol specification, and they also have the ability to introduce faults and test out error conditions. These devices can typically operate in a one-shot method, meaning you typically configure it to perform a transaction or a test, you execute that, and you analyze the results. The results are captured using an analog front end so that you're able to verify both the digital properties of the waveform, the analog properties of the waveform, the timing parameters, the electrical I/O parameters. This is really good when you care about the full stack of the I3C implementation down to the physical layer and up to the higher layers of the protocol. This allows you to understand truly how well your implementation is within the specification. Additionally, these devices may also operate by emulating an I3C controller or I3C target behavior. This is important because sometimes it's necessary to go beyond just generating patterns of I3C waveforms. We actually want to see and examine a device behavior on the bus. And so these devices can help you with that by emulating I3C controller or I3C targets. As of today, there's a few popular protocol analyzers and exercisers available on the market that support I3C. The most popular of which include offerings from Prodigy Technovations, Introspect Technology. Both of these devices are implemented with their own hardware. And there's a solution offered by Soliton, which is actually a software stack running on top of hardware provided by National Instruments. Moving ahead, taking a look at the next category of devices, we'll focus on logic analyzers. Logic analyzers are focused on capturing and analyzing digital waveforms. This can provide some insight into the timing parameters of the bus, but not necessarily all of the ones that can be derived by looking at the actual analog properties of your waveform, including rise time and overshoot, in the typical analog properties of a digital waveform. Those would not be surfaced to you with a logic analyzer, but they're still quite useful. These devices can operate both as one shot, where they're capturing to an onboard memory buffer and then transferring that to desktop-based software to display the solution, or they could also operate in a continuous streaming type of mode, where you're either setting a trigger in which the capture will begin, and in the meantime, you're only observing the real-time decoded data, or that the real-time decoded data is streamed to the host PC where it can be stored in RAM, analyzed later, or even written directly to the hard drive. This allows for very long capture lengths, which can be important if you're examining your I3C bus for, let's say, intermittent errors or sparse events that only occur, 1 out of every 10,000 transactions. This is the type of tool that'll be really beneficial in those situations. Now, it's important to note that the logic analyzer is only a passive device on the bus. It can only sniff the traffic between other devices. It cannot operate as an I3C controller or an I3C target. So unless you have these devices already set up on your test bench, you're going to need something else along with your logic analyzer to make sure that you've actually got traffic to analyze. As of today, some popular logic analyzers with I3C support include the Cellier Logic Pro 8 and Pro 16 devices, and the Acute Travel Logic and Travel Bus Series logic analyzers. In the case of Cellier Logic, the I3C analyzer is a premium add-on that needs to be purchased separately, whereas for Acute Travel Logic Travel Bus, I3C protocol decoding is included as part of the software package offered with the devices at no additional charge. Next up on our list of test equipment, we'll talk briefly about host adapters. Host adapters are focused on providing an interface between the I3C bus and a PC. This is typically done over a USB port, and its goal is to facilitate communications between devices on the bus and your host PC. And so the purpose of this is actually focused on the higher layer orders of the protocol. So for example, these devices are more focused on the actual transaction or the data throughput in high level protocol behavior. They're not so much concerned with the actual timing parameters in the electrical I/O layers of the I3C bus. So these devices aren't providing any analog captures of the actual waveforms themselves. And in many cases, they're not even surfacing the timing properties of the waveform. It's just performing communications and transactions on the bus and presuming that all devices are behaving within the timings requirements of the specification. You'll just see it as a successful communication. You won't really understand how close it is to the edges of the spec, if it's marginal or not. It's just focused on actual sending and receiving of transactions on the bus. Typical use cases for these devices include if you're conducting a test and you want to send a stimulus to your I3C target, you can do that with these devices where you can create all these test cases that might be specific to your actual application. Send the transaction with the host adapter and observe the response that your device is making, either by observing it on a logic analyzer, an oscilloscope, or some other piece of equipment, or just analyzing how it's behaving by setting firmware breakpoints or otherwise, having it set up on your test fixture where you want to observe how it responds. Additionally, these devices can be used to emulate I3C controllers or I3C targets. This has been a common approach for companies who are just early on in the I3C adoption phase, and maybe they haven't yet refined their IP or their custom silicon. They're waiting for that to arrive. And so other engineers can be unbottlenecked by using a test tool like this to emulate the device that they'll eventually get their hands on. And until that's available, they can start doing their other development and testing with a host adapter device. Additionally, these devices find their way into test factory fixtures, test fixtures on the factory. This can be used for automated testing on the line or for provisioning of the bus devices that might be connected to an I3C device on an I3C bus on a capable product that has I3C. As of today, some of the most popular host adapters in this category include an offering from Signalcraft called the Scout SC4420. This is actually a deterministic host controller. Its implementation is based on an FPGA, so it can provide very tight, repeatable waveforms for I3C. And of course, the Vino Supernova, which can provide emulation support for being either an I3C controller or an I3C target. Moving on into our next category of devices, we're actually going to touch upon one of the most versatile, ubiquitous devices on a hardware engineer's desk. And that would be the oscilloscope. We're going to talk about this device, because it's so versatile, in two separate debugging techniques, using it for decoding I3C buses and using it for timing. And we're talking about them separately because this device excels quite well when you use it for one, but not so well suited for the other. So on the topic of decoding, most oscilloscope manufacturers have released software updates for I3C protocol decoding. It's available as a software add-on for most of them. Some manufacturers are even providing I3C decoding built into their software at no additional charge. And the high resolution analog front end of an oscilloscope is very helpful for looking at the analog waveforms. You can see the timings and the quality of your digital transactions, but they often lack a sufficient buffer depth for analyzing the longer transactions that are necessary when you're validating your I3C bus implementation. And so that's a bit of a caveat, but as I mentioned, oscilloscopes are a fantastic device to use for I3C bus validation overall. The high resolution captures are great for looking at the physical layer performance and deriving the electrical I/O properties as well as timing parameters. So almost all oscilloscopes have built-in measurements and timing markers that can make this viable, even if it's a bit manual. And many devices also support implementing this as an automated test, where you can script this using your favorite Visa or GPIB stack, where you can write a script which automatically triggers the capture, exports the data, and then you can run some post-processing on the exported waveform to derive the parameters that you're interested in. Additionally, there's an oscilloscope on the market by Acute Technology, the MSO3124V, which offers built-in I3C electrical verification testing. What this feature does is you point and click in their desktop software, and it just begins to run a capture where it's analyzing all the I3C traffic on the bus over a statistical significant number of transactions. And then from the captured transactions, it's deriving all of the timing parameters for the I3C bus. And it then generates a report. This report not only includes the actual derived parameters, min, max, average, and whether it's within the specification, but it also then generates the scope waveform screenshots representing each of those measurements. So this saves developers a lot of time. They don't need to script all the solution bespoke themselves. It's pretty much ready to go right out of the box. Now with this device, you can perform a subset of the tests that are defined in the I3C Conformance test suite. If the test suite is unfamiliar with you, don't worry. We're going to speak about it later. But it's important to know that while this is possible to use an oscilloscope for timing verification, the end result is just a subset of what can be achieved with a protocol analyzer that we talked about earlier. So the last tool that you'll have in your toolbox are actually the dev boards and evaluation kits from other silicon device manufacturers. Sometimes people don't necessarily think of these as test tools or test equipment because, they're relatively budget friendly. They're not in bulky cases or enclosures. They're just bare boards. But the reality is, in the current state of the I3C market adoption, these devices are a fantastic tool to have in your toolbox as you go about interoperability testing and even just learning about how various implementers have implemented the I3C specification. As of today, many of the latest generation sensors operate as I3C target, most likely not exclusively. Of course, they're supporting backwards compatibility with I2C, and many of them also support SPI. And so you get one sensor that you can operate with from any of these digital communication buses. That's actually quite helpful too if you want to compare and contrast performances of how does this device perform on I3C versus SPI versus I2C. You can really understand and benchmark the advantages that I3C may bring to your application. Today, you'll find devices like temperature sensors that were designed for DDR5 applications, MEMS devices, IMUs, pressure sensors, typically designed for augmented reality or virtual reality applications. They're readily available on the market. You can pick them up from DigiKey, Mouser, or your favorite catalog distributor. One note to be aware of, though, is that there's currently a mix of devices available in this category right now, where some support the I3C v1.0 specification, and others have migrated to supporting I3C v1.1.1. So if you're looking for a particular feature or set of behaviors or supported CCC codes, be sure to check out the data sheets of the targets you're interested in to understand what they've actually implemented for the I3C specification. Beyond the I3C hardened target sensor targets, I'd also like to mention that now there's an 8-bit microcontroller that's available with an I3C target peripheral. This is coming from the folks at Microchip working on the PIC 18F16Q20 device, which is available on a rather friendly development board called the Curiosity Nano. This is great if you actually want to have a fast way to emulate a particular I3C target behavior. You're able to use their example projects, either make some modifications to get them to behave the way you'd like to see, and download the code. And then you've got a quite configurable I3C target, no longer beholden to the implementations of the devices that you can find off the shelf as a sensor category. Here you can kind of make your own bespoke I3C target with, let's say, relatively light lift on the engineering side. So of the devices that exist and are available today, some superlatives that I'd like to call out in terms of the best path to get started. I would say take a look at the ST Micro devices because their documentation is very well done and they provide clear examples. I think that it's probably the most beginner friendly. If you're unfamiliar with hands-on I3C work, starting with a device from ST Micro is a fantastic place to do it because of how much time and effort they've invested into documenting their devices, specifically with I3C. One of the things that you'll notice as manufacturers adopt I3C is sometimes their device might support it quite well. It would be a fantastic implementation, but their application notes haven't yet evolved to support talking about how they've gone about doing it and to really make it as available as the information that they have for their other interfaces such as I2C or SPI. ST's done a great job of making sure that their documentation matches the protocols, regardless of whether it's something they've been supporting for years and years or whether it's the new I3C specification. When it comes to HDR and DDR mode support, so DDR, of course, double data rate, there are few target devices which support that right now. Of course, SDR mode being dominant, but if you take a look at the ICM 42605, which is a 6-axis IMU from TDK and Bensense, their device does support HDR DDR mode of operation. And then, of course, as I mentioned, the user programmability of the 18F16Q20 microcontroller from Microchip. You can get it on a Curiosity Nano board. It's very budget friendly and is a great way to immediately have an I3C target that's configurable. So we just talked a lot about I3C controllers, that are I3C targets that are available, but what about controllers? For the longest time, it was really easy to get a target and really difficult to get a controller up and running. Thankfully, over the past year, many manufacturers have introduced I3C controller peripherals into their flagship product lines. As of today, there's dev boards and evaluation kits available from NXP, ST Micro, and Renaissance, which offer I3C controllers in a variety of different microcontroller cores, spanning from ARM M0s to ARM M85. Of these devices, of course, again, you'll find the same span of minimal documentation to fantastic documentation, same with app notes and support. So you'll want to take a look at what's available for the board that you're going to grab. Of course, I'd like to highlight some superlatives based on my experience, which shows that the STM32H5 available on their Nucleo development board form factor provides the fastest way to get up and running with an I3C controller. They provide some example projects right out of the box that can have you operating an I3C controller in an afternoon. It's a fantastic way to just be able to dip your toes in the water and see what I3C has to offer. This device is limited to SDR mode operation only. So if you're looking for HDR modes, I can direct your attention to the LPC 5536 from NXP, which supports SDR and HDR mode transactions. Along with the LPC line, I believe it's the same IP implemented in all three of them, at least based on what I read in their documentation. And so you can expect that HDR mode support to be also available in the LPC Espresso 860 Max, as well as their IMX RT 600 and 500 series dev boards. And of course, for those who are really eager to dive into the full features of I3C, the latest device release from Renaissance, which is the RA8M1, does include HDR ternary mode support. I haven't yet had the opportunity to play with it myself, but it is fascinating that there's a device available to the general public that already has this advanced I3C feature built into it. Cool. So I just want to highlight here that consider these dev boards and eval kits as one of the many tools that you can use as you go through your journey of implementing I3C spec in your devices, in your end products. Of course, there's not one single test tool that's a silver bullet that's going to solve all of your challenges. You'll likely have a different need for different tools as you go through the journey from the very beginning to the very end of the process. So just keep all these in mind, that they're available to help you make your implementation as robust as possible. Now that we've talked about a lot of the different tools available for debugging I3C implementations, I'd like to talk about a little bit higher level work, which is debugging protocols that are implemented on top of I3C. So the first thing to mention is about debug for I3C. Debug for I3C is a protocol that is on top of I3C, and it's not actually for debugging I3C. In fact, it's a specification developed by the MIPI Alliance Debug Working Group to define a scalable interface to dynamically debug test application processors and other devices over I3C. Basically, you can think of debug for I3C as a way of using functionality similar to JTAG, I2C, and UART all over an I3C bus. The actual details of this implementation are well beyond the scope of my presentation, but Matthias Zenz will be diving into this topic in the presentation that follows mine if you're curious to learn more. I bring up debug for I3C because it's just one of many protocols that are implemented on top of I3C. It's developed by the MIPI Alliance, but there are other protocols that are adopted by other standards organizations and consortiums that are using I3C as the transportation layer for other protocols such as MCTP over I3C, JESD 300-5 serial presence detect, which is making its way into DDR5. ETSI is also developing a protocol on top of I3C. Many others as well are in the pipeline. Implementers and companies that are making their own products are also developing their own proprietary protocols over I3C. And so it's important to know what tools you have available to make this successful. So there are several tools that have built-in support for decoding, debug for I3C, MCTP over I3C, SPD, etc. You'll have to look at each individual tool to see if they support the higher level debugging. And then there's also some tools that feature the capability for end users to implement decoding of their proprietary protocols within the tool itself. As you can see here on the screenshot, this shows the I3C decoding solution from Salier Logic, where you can see the byte level decoding in pink above the data SDA signal, but you can also see the transaction layer decoding above the clock signal in purple, where it's actually showing the meaning of the transaction decoded specifically for the debug for I3C specification. This is implemented using Salier Logic's what they call HLA or high level analyzer extension, where a user can follow the same implementation that's been done for the debug for I3C as it's delivered as a bare Python script. So you can basically use that as a template to implement your own decoder for your proprietary protocol, so it'll show up in the decoded results from the Salier Logic Analyzer. I believe there's other tools in the market that support this as well. Next up, an important topic related to compliance testing. It's important to note that there's no mandatory compliance testing or certification for I3C devices. This lack of certification mandates encourages widespread adoption of I3C. And it's important to know that I3C has a lot of features, but not all of them are mandatory. In fact, many of them are only optional. To know how to make sure that your implementation is compliant, the MIPI I3C working group has defined a mandatory feature set for both I3C controllers and I3C targets. You can find this information on the I3C protocol FAQ page on the MIPI Alliance website. And of course, if you have questions or some part of the specification is unclear, feel free to reach out to the MIPI I3C working group for any clarity you need to ensure that your implementation will work out well with the other solutions that have been implemented by the industry. While compliance testing is not a requirement, conformance testing is highly encouraged. So when we talk about conformance testing, the first thing we need to know is that MIPI I3C working group has defined a set of conformance tests, which is released as the I3C Conformance Test Suite. And this goal of this document is to improve device interoperability. As of this time, it's defined for SDR-only devices because it doesn't include any coverage for the optional I3C capabilities, which includes HDR, DDR, and HDR ternary modes of operation, and as well as some additional features that come along in the optional components of the I3C spec. This will be continued to be developed by the MIPI I3C working group to cover more of the specification in the future. For now, it's important to note, though, that the conformance test suite cannot be performed with digital logic analyzers or host adapters. It requires some analog captures to be able to see the actual timing parameters in some much more high-end equipment than a typical logic analyzer or host adapter can provide. The good news is those who make the protocol exercisers also typically offer software support for implementing and carrying out the I3C conformance test suite. You can see here on the screen that I've included Introspect and Soliton as their options that were easily surfaced to show that they have support for the I3C CTS. And I believe the Prodigy analyzer or exerciser that we talked about in the beginning of this presentation also has support for I3C CTS. I suggest reaching out to those companies directly to learn more about their implementations. So the last thing I'd like to hit on when it comes to the compliance testing or conformance testing is the potential to participate in an interoperability workshop or a plugfest. These events provide invaluable real-world testing opportunities for your I3C devices in a room full of experts across the industry. This I3C interoperability workshop has been hosted annually by MIPI, and it coincides with a quarterly MIPI member meeting. There's no MIPI membership requirements to participate in the plugfest. It is open to anyone. This is really important. I actually participated in the plugfest for the first time before I became a MIPI member. So I can really personally speak to the value of coming in as an outsider and really getting to have this both eye-opening experience to see the best experts in the industry all bringing their devices, their IP together to test out in a confidential environment where you can, basically focus on overcoming the hurdles and challenges you're facing with your I3C implementation and testing it out against a variety of existing implementations. The events are structured quite flexibly. You can work with, you basically sit down as your team, everybody's there in the room, and you can just talk to each other and be like, hey, I'd like to work with you. Can you help me test this? I'd like to test your device with this. At the beginning of the session, everybody kind of talks about, what capabilities their devices have, what they're interested in evaluating, and a really loose test matrix is put together so you can keep track of who you've tested against and who you'd still like to test with. And you basically get typically 2 days worth of time to just dive in and test. I absolutely can't speak highly enough to the value that these workshops provide to implementers. The next I3C interoperability workshop is scheduled for later this year in the week of September 9th. It'll be taking place in Taipei with the Asia member meeting of the MIPI Alliance. All right, that's all I have to say about it. I'd like to go ahead and open the floor up for questions.
Yeah, thank you, Jonathan. That was very interesting. I think really gave a lot of insights on what's available out there and how can you use the tools. So we do have a number of questions. So I'll start to read you the first one. How many targets and controllers can be monitored?
That's a great question. So I would say the number that can be monitored varies by the test equipment, but in general, most of them have a method implemented where as long as the I3C controller is capable of addressing that target, as in, it joins the bus correctly, it gets registered into the device table for the bus, then all of its transactions should be observable by the test equipment. When it comes to the protocol exercisers, I believe there's a certain supported number of devices that it's able to facilitate communications with. But for the most part, you should be able to analyze any device that has properly joined the bus.
Yeah, it does make sense. Yeah. So do you have any recommendations for future-proofing your I3C test tool investment?
That's a great question. I would say that the best way to future-proof your I3C test tool investment would be to speak with the manufacturer before making a purchase, understand what their plans are to support the future evolutions of the I3C specification. As you can imagine, the I3C working group is still developing the specification and evolving it. There will be a specification beyond the existing V1.1.1 So you should take a look at your test tools and see if their manufacturer has stated future support, if that's included in the initial purchase price, or if it's an additional purchase beyond the initial purchase. But I would say that that's probably one of the best ways to do it is to ask about it up front. What's their approach to supporting the evolutions of I3C, since it's something that is going to evolve. Additionally, I would say make sure you're already looking at equipment that supports v1.1.1. I would say that the most notable difference in specifications occurred between the change from v1.0 to v1.1.1. And I think going forward, the changes might be less breaking, to say. And so I think if you're starting off with equipment that's already at v1.1.1 support, the likelihood that they will continue to evolve and support upcoming changes is very high.
Okay, thanks. Yeah, indeed, it was one of my personal questions, if I may. What is the level of support in the version 1.1.1 among the test tools? Do you find it?
I would say right now it's quite high. I think everybody that's invested in supporting I3C in their test tools also continue to invest in evolving with it. I don't believe that there's any device that hasn't yet moved forward to it that we've talked about today, other than the Scout SCT4420. I believe that their implementation is still at v1.0. However, I would suggest check with the manufacturer to confirm that they have not yet released it. But for all the protocol exercisers, they are available for 1.1.1 support already.
Yeah, that's great to hear. So let's go back to the question from the audience. Any sequence for testing the hot join from target to an I3C controller?
Testing hot joins can be complicated because you need to make sure that your controller is already set up, provisioned, so that way when the device tries to hot join, that it actually occurs. Depending on what type of device you're working on, or your role in the device. For example, if you're trying to verify this as a silicon IP, I'd suggest testing hot joins out using an exerciser. That way you have the ability to test all the different edge cases that are possible. Whereas if you're just doing a firmware device driver, and you want to make sure that the hot join is working, I would say hook it up to a controller that you have access to and put it on a logic analyzer and take a look at the waveform just with a digital logic analyzer. I think that would be sufficient to see is the hot join event occurring when you expect it to, based on when you're applying power to the device or when the device enters in its joining mode. But yeah, so I think it really depends on what, how deep you are involved on this particular device. If you're silicon validation, go lower. If you're firmware device driver, skew higher.
So which devices have upstream Linux support?
A great question. I'm actually not 100% sure which of these devices have upstream Linux support. Most of these are microprocessor-based implementations that I covered in my presentation today. As a result, not many of them come with Linux driver support. However, I am aware of some high-end processors that are meant to coexist in the Linux ecosystem that do have I3C device driver support. Unfortunately, I'm not one of the adequate background to speak to this more in depth, specific to I3C device driver support. However, I think if you take a look at the usual suspects that are offering chips into this ecosystem, you'll find that they do have driver support.
Okay, thank you. Sorry about have a little bit of cough. In your experience, which area of I3C think will need more test coverage? Because I3C is quite large set of specification, so there might be some areas maybe are better covered than others.
Yes, that's a great point. Things that need much attention to detail are the things that have changed the most versus a SPI or I2C. So, as another attendee mentioned, hot join is a new capability that you'll want to make sure is being executed by your devices properly, both that the target device is able to execute the flow properly and that your controller is able to handle hot joins. By testing out hot joins, that also has a fair amount of coverage over into the in-band interrupt capabilities, which is, again, a new feature and something that definitely needs an adequate level of detail when it comes to testing and validating that it's working out correctly. And then I would say another thing that takes a fine attention to detail is to look at the call it the synchronous and asynchronous timing features that are supported as part of the I3C specification. The spec provides a way for the protocol to provide some basically time stamping on the data that becomes available from target devices over in-band interrupts. And so verifying that your I3C target is adequately able to track timestamp data. Like, for example, if it wants to send the data over the bus, but the bus is busy with communications to another device, and it's got to hold that data back, but it's in a timing mode where you need to get that timing data out with it. Validating that all of those edge cases are handled properly and you're getting the timing data is accurate to the actual sensor values that are being transmitted. Validating that takes a lot of effort and attention to detail, and it's not something that's really present in SPI or I2C or other digital protocols that you might be familiar with.
Okay, thanks. Great. Somebody's asking if a license is needed to get to use the CTS. Was already answered in the chat. A CTS is free to it's open. Specification can be freely downloaded. Regarding the test tools, was it the voltage coverage? I3C can run from very low voltage to no.
That's a great question.
Yeah.
I would say that the supported voltage varies by test tool. I believe the exercisers can easily go down to 1.0 volts, if not lower. And if you're, of course, analyzing it with an oscilloscope, you'll be able to arbitrarily choose what you want to use as your lowest digital voltage when interpreting your results. The host adapters, logic analyzers all have different input parameters and digital front ends for their captures. But I'd say that most devices can all go down to at least 1.2 volts. Many of them can go to 1.0, and a few of them can go down to 0.8, if not lower.
Okay, well, that's great. Great to hear. In MIPI, we developed the host controller interface specification. If you're aware, does any of the tools use exploit the HCI, especially for the high-level protocol decoding? Do they exploit the HCI feature?
That's a great question. Regrettably, I do not know the answer if any of the test tools are supporting HCI yet. That could be something we could follow up on in a future presentation for sure. I definitely need to do some homework on that one.
Okay, because I think on the same line, somebody was asking whether it's Linux integrated. I think that's probably related to that.
Right.
Thanks, Jonathan. You can get involved whether you're a member or not. I mean, if you're a member, of course, you're welcome to join the I3C working group, or contact MIPI in case of you're interested in becoming we have an adopter and contributor membership. Many of the specifications are available. The I3C basic test tools, host controller interface, and others, discovery, are freely available for download. Only the full I3C, you are required to be a member.